this lesson, we'll learn the important and commonly used techniques in speech processing. Almost all the speech processing uses short-time analysis and windowing. Speech is a slowly time-varying signal over 5 to 100 milliseconds intervals. Over longer interval, 100 milliseconds to 5 seconds. The speech characteristics changes as rapidly as 10 to 20 times per second. The speech waveform is continuous with different kinds of sounds and no well-defined or exact regions where the individual sounds begin and end. Generally, we can divide the speech segment into 3 categories: silence S, unvoiced U, and voiced V. In the short-time speech processing, there are some fundamental assumptions. Properties of the speech signal change relatively slowly with time, about 5 to 10 sounds per second. There is uncertainty due to small amount of data, varying pitch and varying amplitude over very short intervals, 5 to 20 milliseconds. Within the very short segments, the speech can be looked as stationary and can just have fixed pitch and amplitude values. There is uncertainty due to change in sound quality, transitions between sounds, and rapid transients in speech over medium length, 20 to 100 milliseconds intervals. There is uncertainty due to large amount of sound changes over long 100 to 500 milliseconds intervals. There is always uncertainty in short-time measurements and estimates from speech signals. In short-time processing methods, the short segments of the speech signal are isolated and processed as if they were short segments from a sustained sound with fixed non-time varying properties. This short-time processing is periodically repeated for the duration of the waveform. These short analysis segments or analysis frames almost always overlap one another. The results of short-time processing can be a single number, for example, an estimate of the pitch period within the frame, or a set of numbers, an estimate of the formant frequencies for the analysis frame. The end result of the processing is a new time-varying sequence that serves as a new representation of the speech signal. For example, in speech coding, the speech signal is processed with 20 milliseconds analysis frames, which can be divided into 4 5-millisecond subframes. The speech signal is often processed frame by frame in successive windows. The windows can be overlapped in order to eliminate discontinuities in the waveform. For example, the 75% frame overlap hence the frame shift of 1/4 of the frame length. Speech is processed frame by frame in overlapping intervals until entire region of speech is converted by at least one such frame. Results of analysis of individual frames used to derive model parameters in some manner. Representation goes from time sample xn to parameter vector fm. Short-time segments or frames can be obtained by multiplying overlapped windows with different shapes. the frame rate is lower than the sampling rate of the signal. After short-time processing, the speech waveform Xn is represented by speech frame Fm. For a duration of 2 seconds of 4 kHz band-limited speech sampling at 8,000 per second rate, Xn has 16,000 samples. The frame vectors sample at 100 per second rate. One frame can be used for the pitch period estimate, and 12 frames can be used for autocorrelation estimates. Generic short-time processing can be expressed by Qn function, which is a sequence of local weighted average values of the sequence Txn. T is a linear or nonlinear transformation. Wn is window sequence usually with finite length. The windows can be different shapes. Consider 2 types of windows: rectangular window and Hamming window. Rectangular window gives equal weight to all L samples in the window. Hamming window gives most weight to middle samples and tapers off strongly at the beginning and the end of the window. Rectangular and Hamming windows are the 2 commonly used windows in short-time analysis. No windows in the processing can be rectangular windows. They have different frequency responses. The advantage of the rectangular window is that main lobe of the frequency response is relatively concentrated. The disadvantage is that the side lobes are high and there is a spectral leakage. Hamming window is an improved raised cosine window, which makes the side lobes smaller. As the window length increases, the time resolution decreases and the frequency resolution increases. In speech processing, different windows lead to different analysis results. The most commonly used short-time processing technique is STFT, short-time FFT. Firstly, the input signal is divided into different window segments. Then Fourier transform is used to get the frequency response of the speech segments. Sometimes we use short-time power spectrum, which is the square of absolute value of spectrum. Different windows lead to different spectrum. For voice segment, the waveform shows obvious periodic fluctuation structure, and the spectrum shows several peaks, indicating format. For unvoiced segment, the waveform looks like random noise, and the spectrum of white noise approximates straight line. In speech signal processing, firstly, we should pay attention to some questions. What is the width of the analysis window? How to select position of the window? Overlapping? And what is the shape of the window? Weighting the samples. Different settings will lead to different analysis results. Here is an example of obtaining spectrogram with different lengths of windows.
The natural questions that should come to mind at this point are, what about the width of the analysis window, which shows 256 points? Why? Is it the optimal size? What happens if we take a larger window? What happens if we take a smaller window? How do we position these windows along the signal? Do they overlap? And if so, by how much? And what is the shape of the window that we should use? By shape here, I mean the following. Here we're taking chunks of L samples, and just taken a DFT of the raw data. Now suppose my signal is a very smooth signal over this window that goes like this. So this is a smooth signal, and my DFT should have basically just low frequency coefficient. But now remember that to the DFT, everything is a periodic sequence. So what the DFT really sees is something like this. Now here we have all of a sudden a big jump at the discontinuity. And this will create spurious high frequency content in the DFT coefficients. We can counteract this side effect by taking the raw data in each chunk and using a tapering window. So for instance, suppose we have a tapering window shaped like a triangle. We multiply each sample by the value of the window, and we will have a signal that is pretty much identical to the original data in the middle of the window, but then it tapers to 0 at the extremities. And so in the end you would get something without jumps in the periodized version, like so. So the whole story is that we could really spend weeks talking about all the tricks and tweaks that we can apply to a spectrogram in order to extract some kind of information from a real-world signal. But since we don't have that kind of time here, we will just talk about the main trade-off, which is related to the size of the analysis window. Spectrograms can be either wideband or narrowband according to the frequency resolution of the associated DFT. So if we choose a long window, if our L is big, in that case we have a narrowband spectrogram. Why is that? Because a long window will give us more DFT points and therefore more frequency resolution. Remember, the frequency resolution in the end is equal to the sampling frequency divided by L, or 2 pi divided by L if we remain in the complete abstract discrete time world. However, in a long window, more things can happen, and so we have less precision in the time resolution. In the limit, a long window is the DFT of the entire signal, and we have seen that that completely obliterates the time information. Conversely, if we choose a short window, then we have a wideband spectrogram. A short window will create many time slices, because you will divide the whole support of the signal into more chunks. And so we have a much more precise location of the transitions. But a short window will give us fewer DFT points, and so the frequency resolution will be poor. So let's use our DTMF signal once again and look at the difference between a wideband and a narrowband spectrogram. Here is an example of a wideband spectrogram where the analysis window is just 32 samples. With such a short analysis window, we have a very good localization in time of the start and stop point for each burst of sound, but you can see that the frequency bands are extremely wide. Also, having a very short window creates artifacts in the high frequency range, because as we sweep the window over the signal, we will be encompassing uneven numbers of periods for the underlying sinusoids. This is a spectrogram that we saw in the beginning. The window now is 256 points. So let's say that this spectrogram is in between an extremely narrow band and an extremely wide band. This is a very good compromise to interpret what's going on in the signal. If we increase the size of the window to 1024, so 4 times larger, then we have an extremely narrow band spectrogram. You see now that the frequencies are localized extremely precisely. But on the other hand, the time resolution is very poor. We're completely missing the silence here in the beginning, for instance, and the silence between these two digits.
That's all for this session. See you next session.